There are two main sources of noise, namely the mechanical noise, which is also referred to as vibroacoustic noise, and as the name indicates, this is the noise generated by the vibrating structure. And the second main source of noise is the fluid noise, which is also called as aeroacoustic noise. And this is the noise generated by the vibrating structure, by the turbulence in the flow. And for some applications, it's important to study both the aerodynamic and acoustic performance to improve the designs. Yeah, for example, as you can see here, this is the side mirror of a car, and the purpose of the side view mirror is to be able to see the behind of the car from the passenger position. And this does generate a drag, and it also generates noise. So we need to be able to design this in such a way that it generates the least amount of drag and noise for the passengers inside. And to simulate this, we need to consider both the fluid side and as well as the acoustic side. And this is the second example, which is the fan noise. And the fan is designed to blow air from or circulate the air. So we want to be able to circulate the air efficiently, but at the same time, we want to generate the least amount of noise. And this is the one more component of a HVAC system. And this is supposed to flow or push the air to provide the cooling or the effect of the coolant. So we want this to be function efficiently to generate the least amount of noise. So from these applications, we know that it's important to study both the aerodynamic and acoustic analysis, and simulations can help give the performance of these problems. And simulations can help improve the designs by minimizing the number of prototypes as well as the cost reductions by saving the time as well. In this webinar, we're going to talk about how SC-Tetra and Actron can work together. These are two softwares provided by MSC Software to predict aeroacoustic noises. And before going to the presentation, I'm going to talk about both the softwares. SC-Tetra is a general-purpose CFD software developed by Software Cradle, and it's a complete standalone package which has its own pre- and post-processor, and it's based on a finite volume method, and can be used to solve a wide variety of problems ranging from compressible to incompressible. And SC-Tetra can also handle moving elements by using arbitrary Lagrangian layering methods. And the solver is very efficient in terms of memory management and is highly scalable to run on a cluster environment. And it's also proved to be very accurate in terms of the results. And some of the industrial applications where SC-Tetra used are as follows. It is used to predict the external and internal flows of an automotive, as shown here, to predict the drag and lift coefficients to flow over the water jacket or a radiator. And it's also used for a number of industrial machinery equipment like the fans and pumps, and also the ship propeller industry. And these are just some of the problems where SC-Tetra can be used. And Actron is a acoustic analysis software developed by Freefield Technologies. And it uses a finite element method to solve a very large variety of vibroacoustic and aeroacoustic problems, and includes a dedicated user interface for pre- and post-processing. And Actron is used by engineers around the world to improve the acoustic performance of a large variety of products. As you can see from the illustrations, it's able to predict the NVH performance of a car, and the noise generated by the aircraft engine, and the sound produced by the loudspeaker, or the acoustic field loading on a satellite during the space rocket launch. But these are just some of the examples of the capabilities of Actron. And there are actually very few acoustic problems that Actron cannot address. And here are now I'm going to talk about the challenges for aeroacoustic simulation. As you can see from the image here, this shows the static pressure acting on the surface of the car traveling at about 100 kilometers per hour. The dynamic pressure from the fluid flow is about 500 pascals. And to compare that with the acoustic pressure at a noisy intersection of a big city, it generates about 75 decibels of noise. And that translates to acoustic pressure is about 0.1 megapascals, 0.1 pascals. So the scale difference between these two is significant. But whereas in CFD, we have only one pressure value, which combines these two pressures. So there you can see the challenge in simulating this aeroacoustic problem in CFD. So calculating acoustic pressure at the same time as well as dynamic pressure is equivalent to calculating the motion of a stormy sea in which we throw a stone. And in this example, the stormy sea is equivalent to the dynamic pressure, and the stone waves we generate by throwing a stone into this ocean is equivalent to the acoustic pressure. And that's a challenge in simulating aeroacoustic simulation. And now I'm going to talk about the different approaches to solve the aeroacoustic problems. And SC Tetra, a CFD software, can be used to predict the flow-induced noise using the following methods. We have two methods called the sound source detection method and the acoustic analogy method to simulate or to predict the acoustic performance. And hybrid methods, by coupling the SC Tetra with Actran, can also be used to simulate this problem. To give you an idea of how complex these methods are, I'm going to show them in a graph scale. And of these three methods, sound source detection method is the least complex and least expensive, and followed by the acoustic analogy method is a little bit expensive than the sound source method and a little bit complex, and followed by the hybrid method. And this is the level of how the complexity increases. And I'm going to talk about these methods in detail in the next few slides. And sound source detection method is just like a post-processing of the CFD results. And the advantage of this method is that it can use the steady-state results to estimate the noise sources. And we have three methods to estimate the. Actually, there's a video I'm trying to show here, but some. Thanks, Alexis. And there are three different ways we can calculate these sources. One is the Powell-Hoare source method, and the Lilly source method, and the Proudman source method. And the main difference between these three methods are the way we calculate the sources. And the Powell-Hoare source method uses the vorticity and the velocity vectors to calculate the sources. And the Lilly source method just uses the velocity vectors to estimate the sources. And whereas the Proudman source uses the turbulence to estimate the sources. And here is an example showing the source estimation using the Proudman source for a flow in automotive. And the first step we do is that establish a steady-state solution and then use the flow field to estimate the sources. And for a flow in automotive, we know that Alexis, can you play the animation again? We can see that the main sources are coming from the side view mirror and Alexis, can you play the animation?
Yes, sure.
Thank you. So here we're establishing the flow field from a steady-state solution, and once the flow field is established, we do this post-processing to find out where the sources are. And this is one of the main sources of the noise of the flow around the automotive. And then we do have some small sources behind the vortex shedding behind the automotive. And then we have additional sources for the flow through this radiator grill, the bumper in the front. And then we also have some additional sources under the hood. So this method gives us a qualitative approach to compare different models. And the second method we talk about is the acoustic analogy method. And the reason why this is a little bit complex compared to the previous method is that this method uses an unsteady solution to calculate the acoustic pressure. As we mentioned, the acoustic pressure is much smaller compared to the dynamic pressure from CFD. So we use an expression expression called FWH equation to estimate the dynamic acoustic pressure, and we use this dynamic acoustic pressure to calculate the sound pressure levels. And to be able to use this method, we need to consider that the sound source should be compact, and at the same time, the observation point where we record the sound pressure should be far away from the sound source condition. And here is an example showing that. So here is a flow over a cylinder, and where the cylinder is the source of the noise, and the observation point is much far away, as shown here. And the sound pressure level is recorded based on the transient simulation, and then that is converted to a frequency domain by doing the first Fourier transformation. And there is a limitation in terms of how we can use this method, because in CFD we cannot handle the reflection or propagation of the waves through the structure. So if you want to handle all these scenarios, we need to go for a hybrid method. And Alexis is going to take over from here and present the hybrid methods. And Alexis.
Yeah, thank you, Sunil. Yeah. So from there, now that we know what can be done in CFD, we would like to present you what we can do with what we call the hybrid method. So we are using first ST-tetra to compute the steady and then unsteady flow. And then we will have our CFD calculation set up as usual. We will just request an export of files in CGNS format. And this CGNS file can be transferred to Actron. And from there, Actron will compute the aeroacoustic sources caused by the turbulent flow, and then the acoustic propagation from these sources to the locations of interest. So the complete aeroacoustic calculation with ST-tetra and Actron can be performed according to two different workflows. And the choice between these two workflows will be driven by a trade-off between accuracy and computation time. The first workflow uses ST-tetra and Actron aeroacoustics. So ST-tetra runs a steady state analysis and then an unsteady flow analysis. Actron reads the unsteady flow results and is able to compute the aeroacoustic sources. Once we have these aeroacoustic sources, we can compute the acoustic propagation and obtain very predictive, accurate acoustic results. You will see later during the presentation with an example how accurate this method can be. And the second workflow that we have available is using ST-tetra and Actron SNGR. So ST-tetra this time only runs a steady state analysis, and Actron SNGR is able to compute the aeroacoustic sources from the steady state flow results using a stochastic reconstruction method. So since it is no longer needed to run an unsteady analysis, this workflow is much faster. It's also less accurate in terms of absolute values, but still able to represent very well the relative performances of the different designs. So if you have several designs you want to rank, or if you want to perform an optimization, you will certainly prefer this workflow. And from these two workflows, you can understand that the critical part is the interface between CFD and acoustics. So ST-tetra computes the flow. This is usual for ST-tetra. Actron computes the acoustic propagation. This is also very standard for Actron. The question is, how are the aeroacoustic sources computed from the CFD results? So the aeroacoustic sources are computed using what we call an aeroacoustic analogy. So these analogies are based on one main assumption, which is that turbulent flows create an acoustic field, but the created acoustic field does not have any effect on the flow. So as you remember from the introduction that Sunil gave, the pressure fluctuation of the acoustic fields are extremely small compared to the fluctuation created by the flow. So in most cases, this assumption is valid. There are only very few specific cases that do not satisfy this hypothesis. In particular, I think about the combustion, where the acoustic field has an influence on the flame pattern. But otherwise, this assumption is the key ingredient that is allowing us to compute the aeroacoustic performances with this two-step approach. Step 1, compute the unsteady flow using ST-tetra. And step 2, extract the sources and do the acoustic propagation with Actron. So to give you a little more details, there are two different acoustic analogies that can be used in Actron. The light hill analogy, which is valid for low Mach numbers, and the mirroring analogy, which is valid for higher Mach numbers. So let's have a look in more details at how these aeroacoustic sources are computed. I will explain based on light hill analogy because it's much simpler. Simply because it's much simpler. So both light hill and mirroring analogies are based on Navier-Stokes equations and continuity equations, which are the equations that are used in CFD. For the light hill analogy, we are considering this equation without mean flow, and that's why this analogy is used for low Mach number, and that's why also it's simpler to explain. These equations are then rearranged and combined in such a way that we can see a wave operator appear on the left-hand side of the equation. And then we take everything that is on the right-hand side and we say that this is our source term. And this source term is depending on the density and the fluid velocity. So what Actron does is that it computes this source term based on the velocity and density fields, and then it can compute the acoustic propagation from these sources anywhere around. So you can understand that we are starting from the equations that are used in CFD, only making few assumptions, and we are able to compute a source term that is representing the aeroacoustic excitation. So now that we know in little more details how it works, let's review the entire simulation process. So we have seen that the key ingredients, the ingredients that we need to go from CFD to acoustics, are the fluid velocity and the density fields in the regions where turbulences are present. We have seen also previously that there are two workflows possible. The first one is using SC-tetra and aeroacoustic. And when we use this workflow, we can directly get from the unsteady CFD analysis time-dependent fluid velocity and density fields that will directly be used for the aeroacoustic source computation. The second workflow is using SC-tetra and Actron SNGR. With this workflow, we can only get a mean velocity and a mean density field, which is not time dependent. So we cannot directly use it to compute the aeroacoustic sources. And this is where Actron SNGR method is used. So based on these mean velocity and mean density fields, and also using information output by the steady state analysis regarding the turbulence, these are, for example, the turbulent kinetic energy or the turbulent dissipation rate, Actron SNGR is able to reconstruct a time-dependent velocity field based on a stochastic reconstruction method. And then we have our time-dependent velocity field and our density field. So I won't give you more details regarding how SNGR works. We did a webinar recently about that, so I really encourage you to go and watch this webinar if you want to know more about this method. So once we have these time-dependent velocity and density fields available, Actron will compute the aeroacoustic sources. These aeroacoustic sources can be visualized in Actron, which is already a very interesting indication on the locations where the noise is generated. You can have indication on the locations where maybe the design should be adjusted. So this is the first thing. We have our aeroacoustic sources, which are on the CFD mesh. Now, what we have to do is to map these aeroacoustic sources from the CFD mesh to the acoustic mesh, which is much coarser. And this process is done through an integration method where the values at each node of the acoustic mesh are computed based on the results from all neighboring CFD cells. This method is very accurate because it uses all the information contained in the CFD mesh, and it doesn't require to refine the acoustic mesh in the region of the source, so it's also very efficient. Once we have these aeroacoustic sources mapped on the acoustic mesh, well, we can run the acoustic calculation with Actron. These sources will be used as excitation, and then the acoustic propagation will be computed. What is very important aspect here is that with this process, the Actron calculation is not limited to simple acoustic propagation. It can contain any component or boundary condition that is available in the different Actron modules. So you can compute the acoustic propagation through complex propagation paths. You can add absorbing materials, perforated plates. You can compute the vibration of a structure due to these sources, and so on. So a lot of different things you can do, and a lot of different applications you can address. So you are able to predict the noise, but also to test some countermeasures that will help reducing this noise. So if you want to summarize this process, I would say that the hybrid method allows to get the best out of each software. We know that SC-Tetra is good at doing flow calculation. Well, we ask SC-Tetra to compute the flow without caring about acoustics. Then Actron is handling the acoustic part with all these particularities without having to care about the flow calculation. So the resulting process is flexible and is able to provide more information on the aeroacoustic source generation and the acoustic propagation. But of course, all this process would not be useful if it wasn't accurate. So to demonstrate you that the process I presented you is accurate, I would like to show you an experimental validation of Actron Aeroacoustics that was done by Hanon Systems and presented at SAE International Conference in 2009. So Hanon System is designing air conditioning system for cars, and their interest was to use a method that could predict the aeroacoustic noise. So we suggested them to use the hybrid method that I presented you, and then they performed an experimental validation of the method. So the case that they studied is a simple air conditioning duct. The air is injected through the system, and a microphone is located in front of the pipe to record the aeroacoustic noise. So to reproduce this experiment, an unsteady CFD calculation is run, and then an Actron model is built. You can see on the top right corner the aeroacoustic sources, and then the pressure computed by Actron. And as you can see on this plot, the results that they were able to obtain were matching very well between the experiment and Actron. And these results convinced Hanon system engineers that the method that was well suited to predict aeroacoustic noise. So before concluding this presentation, Sunil and I would like to show you how such an aeroacoustic calculation process can be carried out with a demonstration example. So we chose to work on a motorcycle exhaust muffler, where typically we try to reduce as much as possible flow noise. So I will let Sunil present the steps in SC-Tetra, and then I will show you the Actron model. So Sunil, you can take over from here.
Yeah. Basically, as we explained before, there are 3 steps we do, or when we do the CFD for aeroacoustics. The first step we do is typically establish the flow using a steady state simulation, and we use this as a base for everything we do later on. One, establish the mesh resolution for acoustic analysis, and establish the time step we want to use for transient simulation and all these things. So steady state simulation we do is the main basis for the future simulations we do for aeroacoustics. Once that part is done, we do the initial transient simulation where we clear the initial turbulence, which is generated by numerical error or anything. And after we finish the first transient simulation, the final transient simulation is the one where we generate the samples, which we're going to use for acoustic sources prediction. And to keep things simple, and I'm going to show you the operations on how we set a case for step 3 here. We start with a model and walk you through the steps on how we can set a case or set the boundary conditions and all the other parameters for the solver. So we launch our software through the Kicker, and that's the Kicker, and we launch our preprocessor. We have different modules, and once we open the preprocessor, we can open our model file, which is the native format for our SC-Tetra. And typically, the first step we do is we define the regions, but for this demo, we prepare the model. So I'm just showing where the inlet is and where the outlet and where the wall regions are. And pretty much the entire surface of the muffler is a wall here. And to set the boundary conditions, we go to the analysis condition wizard and select the condition wizard. And it's a wizard-driven boundary conditions, so it will walk you through the steps. And the first step we want to do is enable the larger D simulation model for the simulation, and we're going to choose options for the larger D simulation. And as you can see on the right-hand side, you can see the options will be enabled and disabled based on what we choose, and they will be added to the left-hand side tab. The second step is we set the time step for the simulation. And for this case, we calculate that we need to simulate about 0.1 seconds. So using a time step of 5 microseconds, we need to simulate 20,000 time steps. And to set the properties of this fluid, working fluid, it's exhaust gas, and we specify the properties. And for this demonstration, we're just going to set this as an incompressible flow. So we give the properties equivalent to the temperature. So once we enter all the values, we can just click OK to register this material property in the database, and we can use it for the future purposes. And this material property will be applied, and we're going to use it, and we can go to the. We're not going to use any initial condition because this is going to be restart simulation, so we can skip all those, and we can definitely go to the boundary conditions. And we're going to specify a mass flow rate condition. And we choose the mass flow rate to have a exhaust Mach number of about 0.1. And the outlet is set as static pressure 0. And then we have the rest of the walls set as stationary walls where there is no slip allowed. And then under the solver settings, we can tighten the convergence or the criteria for between the time steps, where we reduce the relative error to 1 × 6 and increase the number of iterations. And in addition to this, we also need to make sure that we use a second-order implicit scheme for the time derivative term to calculate the results a little bit more accurately. And under the output control, we can request the aeroacoustic analysis for the CGNS files for the aeroacoustic analysis. And the frequency here is about 48 time steps, which is about 200 microseconds. And we can choose the software for which we want to export the data to. And finally, we can specify the file names we want to write this data to, and that pretty much completes the setup. So once we're done with this, we can save this as an analysis condition file called an S file. And FLD file is the field data for the CFD results. So in this case, we're running the simulation to get the data for acoustics. So I just choose the option not to write it. And we give a file name, and that completes the setup for CFD. So once we're done with this simulation, we run this and generate the data. And from then on, Alex is going to explain how we handle the data for Actron.
Thank you, Sunil. So back again to our two workflows. Actually, before we move forward, I just wanted to mention something more. I talked about flexibility earlier during the presentation. And basically what we are doing here with Sunil is an illustration of this flexibility for this hybrid method. Sunil has skills in CFD, knows how to use SCTitra very well. Well, he's doing this flow part. And I know about acoustics, so I'm taking over his file, and I can move forward with the process, and only focus on the acoustic part. So this is also the kind of flexibility that this workflow is providing. Just to show you some numbers here that demonstrate once again the differences between the two workflows. The first workflow with Actron Aeroacoustics requires this unsteady CFD calculation. You can see that the analysis time is fairly long, and the amount of data that we have to transfer is also significant. So this is to get very accurate results. If you want to have relative results, so comparison between different designs, you don't need to run the unsteady flow calculation. You can go with the second workflow, and you can see that the computation time and the amount of data exchanged is much, much smaller. So let's actually jump to Actron now. I already loaded in Actron VI, which is Actron pre and post processor, the analysis that we are going to set up for this case. As you can see, we have an acoustic mesh. What is interesting is that this acoustic mesh, which is coarser than the CFD mesh, we don't want to use the same mesh. So this acoustic mesh can be created from the geometry of the muffler, but it can also be created directly from the CFD mesh. You can import the CFD mesh, remesh it with coarser element size, and this allows you to create the acoustic mesh. So looking at the analysis, here we have, it's quite small I guess, but here is a direct frequency response analysis. So we will solve the problem frequency per frequency from 100 Hz to 2000 Hz with a step of 10 Hz. And you can see that this analysis is fairly simple. There are 4 components and 1 boundary condition. The first component we are looking at is this duct here, which is basically the inlet of our system. And what is interesting to note here is that we have a propagating mode -1, which is free. This means that every acoustic wave that comes across this surface in the direction towards the, leaving the system, will not be reflected, will be allowed to just disappear at this boundary. Then we have our, what I call interior acoustics. This is just an acoustic region, which refers to this exhaust gas material. Actually, we could have spatially dependent material properties according to SC-tetra calculation results. And this is how it looks like. So we have a 3D mesh, which is basically the entire muffler here, so inside, and also part of the outside to capture the jet here. So this is our acoustic component, and we have our light hill volume boundary condition. So basically, this is where our sources will be. And this refers to the aeroacoustic sources that we already computed. Around this, we have a second acoustic domain. This acoustic domain is just there to ensure that the acoustic wave can propagate around the muffler. And on top of that, we have an infinite element surface. This will let all the acoustic waves go out of the system without any reflection, so a non-reflective boundary condition. And this will also allow us to get results on this array of virtual microphones, which are located outside of the computation of the mesh that is used for the computation. So this is a typical model for Actron aeroacoustics. If we go back to the slides, we can see the results. So this is the sound pressure level at 1 microphone location for the 2 different cases that we computed, so 2 different Mach numbers. For example, we can see that we have a peak here at 800 Hz, so we can maybe investigate what happens there. And we can see that there are some aeroacoustic sources that are located at this particular location in the pipe. And looking at the acoustic propagation as pressure, you can see that, okay, maybe, yes. There is kind of an acoustic mode between this chamber here and the pipe. And since the aeroacoustic sources are located at a maximum of this node, it will produce a lot of noise. And that's why we can see this peak here. So this is it, I think, for the demo. This concludes our presentation. I hope that we are able to show you that using a hybrid method, you can get the most out of STT-TRA and Actron to improve both your aerodynamic and acoustic performances. So we ask STT-TRA to compute the flow, which it can do very efficiently and accurately. Then we use the results from STT-TRA to compute the aeroacoustic sources and the acoustic propagation in Actron. This approach provides a lot of flexibility and, most importantly, reliable results that will allow you to improve the design of your products earlier in the design phase and with less prototypes.